Hello everyone. In this video we are going to talk about the nonlinear pendulum. So as you know, if we have a simple model of a pendulum, which is a mass hanging from a point and no damping on the joint, so the pendulum is only affected by its own gravity and the tension in the cable, then there are only two forces acting on it, right? There is this force T and mg, and mg you can break it down into two components, right? And if you want, you can call this angle either theta or alpha, right? Since my notations is all based on theta, let me change this angle to theta as well. So if you call the deviation from the vertical direction, if you call it theta, then if you write some of the moments about this point O and go with counterclockwise positive direction, T passes through O, it has no moment, and between the two components of mg cosine also passes through point O, so it's only mg sine. And clearly you see this force creates a clockwise moment while theta is counterclockwise, so the moment is negative and the distance is L, so this is going to be negative mg sine of theta times L, and this is equal to I about point O times alpha, and alpha here is theta double dot, the angular acceleration. Now, what is I of a mass m, a distance L, a discrete mass, right? Not a continuous mass from distributed mass from point O. This is simply ml squared, right? And so now you can simplify 1m and 1l from both sides. If you do so, the governing equation becomes theta double dot equals negative g over L sine theta. And this is the governing equation for the pendulum, which is subjected to two initial conditions. Theta at time 0 is equal to theta naught, the angle at which you release it, and then theta dot at time 0 is equal to omega naught. Most of the time you try to solve it when omega naught is 0. So you bring the pendulum to angle theta 0, whatever angle it is, and then release it from rest. So most of the time you might consider this omega naught equal to 0. The problem is this is a second order ODE and it's nonlinear because of sine of theta. If somebody says what is theta as a function of time here, could you solve this very simple ODE? It looks very simple. Could you solve it for me if I give you two initial conditions? The answer is unfortunately you cannot. There is no analytical solution whatsoever that so far our mathematicians could find to get this theta in a closed form solution with a limited number of terms. The only thing you can do is to approximate this theta, and the reason is the solution is an infinite series, and since you cannot really keep adding terms together forever, you have to stop at some point, and anywhere you stop there will be approximation. Okay, so there is no closed form solution with a limited number of terms. And mathematically, I forgot the name of the mathematician, but he showed that there is none of the functions we know in math that can, if you plug it into this ODE, it will fit. Okay, so in general, the nonlinear pendulum has no solution as, again, limited number of terms, closed form for theta of t. So the only way we can solve it is numerically. So I can go, let's say, create a Simulink block like this. And here, this block here, this signal is the theta double dot, right? So this is like theta 2 dot. And integrate it to get theta dot. And then integrate it one more time to get theta. Then feed that theta back through this trigonometry block to get sine of theta and multiply it by negative g over L to get what? Back theta double dots, right? So we can solve it numerically, of course. and just you need to pass to it some initial theta 0 and some initial omega naught. In this case, as I said, I use 0, release it from rest, and look at the solution, numerical solution. So what we do in linear vibrations, what we do, we assume that this theta is small, or theta naught. If you release it, let's say if this is 0, we assume this release angle is a small angle. Okay, it's less than 1 radians quite a bit, typically somewhere like less than 6 degrees. If that's the case, we can approximate sine of theta by theta. So now it becomes a linear second order ODE, and then there is a solution for theta in this case. Theta here is going to be theta naught times cosine of omega n t, where omega n is basically the square of this coefficient. Okay, the square root of this coefficient is the square root of g over L. Okay, so if only there is this assumption that you don't really release it from a large angle, then you can, yes, have something. And if that's the case, then the period of the oscillation t, which is 2 pi over omega n, is going to be 2 pi, right, times the square root of L over G, correct? And this is constant. So if a pendulum is linear, the period of the oscillation is what? Is almost a constant value. It does not depend from what angle you release it, whether it's 1 degree or 2 degrees or 3 degrees. Almost, you can say that what? You can say that the period of the oscillation is what? Is a constant value. But in nonlinear pendulum, when this assumption is not valid and there is the sine of theta and there is no solution, the question is there any way I can find the period of the oscillation? By the way, this period and that tension are two different things, okay? So let me just call it tension. So this T, or I can call it maybe f of t, something like that. So is there a formula? And you might say, well, if I cannot find theta, then how can I find the period for it? That's right. You cannot find a closed form with limited number of term formula for t. If you find, then again, it's going to be an infinite series. But the question is, fine, could you give me that infinite series? If I want to approximate at least this t, do I have any approximation? The answer is yes. How can we do it? Let me show you. So here I'm going to show you how to find the period of a nonlinear pendulum. So here we use the work energy method and we calculate the kinetic energy, which is 1/2 mv squared. Now, since the pendulum goes on a circle, v equals r omega, right? So the v is going to be in this direction, right? And v equals r omega. Now r equals L, and omega is theta dot, so it's going to be 1/2 m L squared theta dot squared. That's kinetic energy. Potential energy, you need the datum, and here for the datum we use the bottom point. Okay, so what we do is we consider the very bottom of the pendulum, where it goes at the bottom. And so at the bottom here we assume that potential energy equals 0. So in order to find it at angle theta, we need to find this vertical displacement. And you know that if this is theta, then this distance here, from here to here, this is L cosine of theta. And this whole distance from this point to this point, that is L, right? So this distance from here to here is L. So this guy here is going to be L times 1 minus cosine theta. And if you multiply that by mg, then you will get the potential energy. Now, mechanical energy is sum of the kinetic and the potential, so you add them together. And since there is no damping in the system, the mechanical energy, there is no waste of energy, the mechanical energy will be conserved. You have conservation of mechanical energy. So one thing we do first, before we go to that part, we define this G over L omega squared, so that is the natural frequency of the linear pendulum, right? Remember, omega n was the square root of G over L. If you do that, then we can get rid of a bunch of these M's and L's. So what we do is we divide both sides of this relation by ml squared. So we get E over ml squared equals what? This term will be 1/2 theta dot squared. This term here, it needs one L at the denominator, right? Because it only has one L, so it is going to be G over L, and G over L is omega squared. So it's going to be omega squared times 1 minus cosine theta. Okay, and then you take the positive omega squared to the other side, you get negative omega squared, and then negative omega squared cosine of theta, you keep it on this side. So you'll get this term here. Now, and this is of course constant because E is constant and omega n is constant square root G over L. So that whole thing is constant, this one. This left-hand side equals to a constant. Now, in order to approximate this E and approximate this, not approximate, calculate really. In order to calculate E and calculate this constant, we said that E is constant. It doesn't matter at which point along the motion of this pendulum you calculated. E for all points is the same. So we calculated when you release it from rest at angle theta naught. So we take it to theta naught, release it from rest, so there is no kinetic energy. Potential energy is equal to this much, right? Just plug in theta equal theta naught there. As I said, no kinetic energy here. And then this is your E. And for, again, if you divide it by ml squared, you can also write it as ml squared omega squared. So now I plug this E into this top relation. The ml squared will be cancelled. Okay, so what you will get is 1 minus cosine theta times omega squared and then minus omega squared. So this term here becomes omega squared times 1 minus cosine of theta naught. And then look here, there is another omega naught. So that omega naught and this one will cancel. So you just get negative omega squared cosine theta naught. And the left side is still there. So now what would you do? This is clearly a first order differential equation. Remember, this whole thing is a constant. And this is basically, this omega, you have to be careful about it. And this omega is not really theta dot. This omega here is omega n. So it's better to call this omega n instead of all the places we called it omega. Let's call it omega n. This is a constant number. It's not time derivative of your angle. It's not a variable thing. It's a constant thing. Okay, so now if you look, here is a first order differential equation, as I said, but it's nonlinear. There is no solution for that. And the way you take care of it is, let me add this omega n all into place. The way you do it is you take this term to the other side. So you'll get what? You'll get 1/2 theta dot squared equals, both of them share omega n, so it's going to be omega n squared times cosine of theta minus cosine of theta naught. Okay, and then this term in the parentheses, you use trigonometry equalities, and you say the cosine of theta minus cosine theta naught equals 2 times sine squared of theta naught over 2 minus sine squared of theta over 2. And you plug it into here, right? So this becomes 2 times sine squared of theta naught over 2 minus sine squared of theta over 2. Now, you multiply both sides by a 2, so this guy becomes a what? This guy becomes a 4. And then you take a square root. So you'll get what? You'll get theta dot equals omega n, right, times square root of that whole thing in the parentheses, this one. Let me plug it down here for you. Or actually, it's better to just write it. So let me write it. Now this theta dot is d theta over dt. Remember, this guy is d theta over dt. So let's go ahead and write that term as well. And then what we do is we are going to take a reciprocal from both sides and then do the separation of variables. If you do that, then you'll get dt equals, that guy goes into the denominator, d theta goes to numerator, and if you do that, you will get this one here. You will get this. Okay, of course, remember that 4 also becomes a 2 here, so you get 2 omega n. Let me clean this part up, right? That 4, when you take a square root, you'll get a 2. Okay, and that 2 is, so you'll get this one really, okay? And if you see here, let me write the previous step to it. So you get dt equals d theta over, and then you'll get 2 omega n and then the square root term. This is what you will get. Let me write, because several of the intermediate steps are missing in these notes, so I want to make sure you have it all. Now you would integrate both sides. This guy goes from basically 0 to theta naught. This guy goes from 0 to t over 4. Because when you go from 0 to theta naught or theta naught to 0, all you do is 1/4 of the oscillation. The other quarter you go up, then you go back here, then you go back to where you started. So that's really 1/4 of the period. And so now this side is simply going to be t over 4. That side stays. Now we multiply both sides by a 4. If you do that, this guy will go away. The 4 and that 2 will simplify, and this 2 will come to the numerator. And you can get this 2 over omega n term out, and then you'll get this term here. Then you'll get this one in the box. Okay, so now you have this. The problem is, can I take this integral? Is there any solution to this integral? And the answer is no. This integral, there is no analytical formula for it, unfortunately. Another way to relate it to what you might know from math is, here we define the square root of this constant, right, or the sine of theta naught over 2, we define it as constant k. If you define it like that, and you change your variable from sine of theta over 2 to z, where z is sine of theta over 2 divided by k. In other words, sine of theta over 2, this guy equals k times z. Then you can write that integral into this format. That you can write it like this, and you might say, where does that come from? Well, let me show you that one as well. So what we did was, and here I need to do a little bit of cleanup if you don't mind. We did some change of the variable and we converted our integral into this bottom format. How come? Let me show you. So if I write this, it's going to be 2 over omega n. This integral goes from what? Now remember, you change variable to what? To z. So now the limits should be based on z. And how do we find them? Well, when theta is 0, this is going to be 0 over something, so z also is going to be 0. When theta equals theta naught, then you get sine of theta naught over 2 over sine of theta naught over 2, so z is going to be 1. Okay, so the limits of 0 and theta naught will be 0 and 1 for z. Then the square root is going to be what? So what I can do, I can factor out a sine of theta squared, sine squared of theta naught squared. I can factor it out and bring it out. So it will be sine of theta naught over 2 times square root of, this is the theta, 1 minus sine squared of theta over 2 over sine squared of theta naught over 2. Okay, so here I factored out this term and bring it out. Now what do I have? Well, if you look here, this guy is z squared. Okay, that guy is z squared. What about the rest of it? So what is d theta? Here we have to find d theta, and remember, from this change of variable, sine of theta over 2 is equal to what? By the way, this guy is k. Sine of theta over 2 equals k times z. So what I can do is, I can take a differential from both sides. It's going to be 1/2 cosine of theta over 2 d theta equals k dz. And what is cosine of theta over 2? What I can do is to write it as square root of 1 minus sine of theta over 2 squared d theta. This is equal to k times dz. Now, remember, sine of theta over 2 is kz, so this is going to be 1 minus kz squared. Right? So d theta becomes what? D theta becomes 2 times k dz over square root of 1 minus what? K squared z squared. And if you plug that up here, that d theta has a k, and there is this k here, so those two k's will be simplified, right? Remember that d theta was what? It was k dz divided by 2k dz divided by the square root. So this k and this k will be simplified. That 2, right? And that 2 will be multiplied, so you'll get a 4. The omega n is still there. And the rest of it is going to be dz over what? Here it's 1 minus z squared times 1 minus kz squared, both under square root, and that's what you can see here. So you'll convert your integral into this, and this is a well-known integral called first elliptic integral. And first elliptic integral, we know in math there is no closed form with limited number of term solution to it. But we can approximate it with an infinite series, and the infinite series to approximate it is this guy. Now remember, what was your omega n? Omega n is what? Omega n is square root of G over L. So when you bring it to the numerator, it's going to be L over G. And by the way, that whole integral is not really that series at the bottom. There is some constant difference between them because you see your 4 is converted into 2 pi. So 4 times that integral equals 2 pi times this series. Okay, or in other words, that integral equals 2 pi over 4 or pi over 2 times this infinite series. Inside this infinite series, the term k is what? That sine of half initial angle. So you can find the period of what? Of a nonlinear pendulum through this infinite series, with again k is what? Sine of half initial angle. And L and G are clear, the length of the pendulum and the gravitational acceleration. Okay, so you can find it through this, and the more terms you use, the better and better you are going to be at estimating the period of a nonlinear pendulum. These terms, when they go further, they get smaller and smaller, because as you can see, the k is always less than 1, okay, because it's sine of something. And so when the powers go bigger and bigger, the terms get smaller and smaller. So the major contributions are the first few terms, but as you get more and add more and more terms, you change the decimals, basically, the fine decimals, and you get better and better, but the contributions are not super large. Now, to simulate that for you, here I made this pendulum, as I said, this nonlinear pendulum, but here I'm allowing theta not to change. I'm taking it as a parameter. So in my MATLAB code that I wrote, what I did, I tried lots of different initial angles, 1 degree, 3 degrees, 5 degrees, and then from 10 degrees to 90 degrees with 10 degrees apart. So my angles, initial angles are 1, 3, 5, 10, 20, 30, all the way to 90. I have a bunch of angles here, initial angles. For each one of them, I run my Simulink. And of course, since my Simulink is using the sine block, so I make sure that I convert those degrees into radians here before passing it to them. And then when I get the data out, so this scope block, let me show you. This scope block here, you see the oscillations of the nonlinear pendulum, and you might be tempted to say, well, this is like a sine function or a cosine function. Yes, but not exactly, okay? This is what we call a pseudo-harmonic function, and it's not really a simple sine and cosine. As I said, if you plug in a sine or cosine into the governing OD, it will not work. So I export my data to the workspace. You can see under the name theta. And the question is, how do I find a period? Right, because I need to find a period through the simulations here. So what I do is I look when the plot passes 0. How do I do that? Well, this plot is made of lots of points. Remember here, I'm sampling this plot at 1,000 data points per second. So anytime each data point and the next data point have different signs, positive, negative, or negative, positive, that means I crossed a 0. Okay, so I use that fact and I find all of the points that this function passes through value of 0, all the roots basically. And that's what I did in my function, in the utility function that finds the period. You see here, the second column of theta are the angles, the first column are the time points. So I look at the second column where each number times the next one is negative, which means you are passing 0, and I record that as a crossing point. Then how do I find the period? I subtract the first crossing point from the third one, and that's my period. Why? Because if you look back here at this scope, if this is the first one, this is the second one, this is the third one, it's the third time and the first time that correspond to one period. So I subtract them, take an absolute value, because I subtracted 1 from 3. If you subtract 3 from 1, you don't need the absolute value. And I return it back to my calling function. And I record it as a relatively accurate estimate of the period through simulation. I also calculate the value of this formula through what? Through using only one point of the series, so just one. Then I use two terms, 1 plus k squared over 4 times that, and then I use three forms, all 3 times that. And I call them what? I call them t underscore 1, 2, and 3, and my goal is to compare these approximations with the one I get from the simulation and see how they are different. And here is the result. By the way, let me show you one thing before I discuss the result. So the interesting part is this. If I only use one term, right? So if I just use one term, what is this? This is exactly the formula that we had. Remember, I told you that if you use the linear pendulum, omega n is what? Square root g over L, huh? So look here. Remember, period is what? Is 2 pi over omega. And omega n is what? Square root g over L. So if you bring it up, you'll get that. You see? So the first term here, which is constant, that's the period of a linear pendulum. But if you want a nonlinear pendulum, you have to add those other terms to make it what? To make it more and more accurate. So as I said, this is the final result that you can see. The blue is the one from simulation, the relatively accurate one. Red is if I only use a constant, a linear pendulum, and you see it doesn't change. Black is with 2 terms, and green is with 3 terms. And you see if I use more and more terms, my approximations are getting closer to the simulation values, or you might call the actual. It's not really actual, but I would say more accurate. And you can see that in the low range, in small initial angles, they are all on the top of each other. If you look, if I zoom in, you see in the range of small angles, all of them are the same. You see it's roughly up to 4 or 5 degrees or so. Up to somewhere like 4 or 5, even maybe 6 degrees. You see the difference is not huge. The red curve, which is the simple formula, and the blue one, which is the simulated one, are almost on the top of each other. So you see below 6 degrees up to 5 degrees, the simple formula is very good, the constant. But after that, the red curve and the blue curve deviate substantially. And as the angle gets bigger and bigger, this deviation gets bigger and bigger. Okay, so if you want to approximate the period of a nonlinear pendulum with big starting angles, you definitely need to use what? This formula, and you need to use more and more terms if you want more accurate. 3 terms is not really bad, but if you want, you can use more terms, and all you need to do is to see what is the elliptic integral series, right? If you just search it up, you can add more terms, okay? So if you want to know one extra term, I can add one extra term for you. Again, all you need to look for is what we call elliptic function. So if you want the next term, it's basically 15 squared, or like 225. Let's see if my marker works here. So it's going to be, as I said, 225. 15 squared divided by 48 squared times K6. So if you're looking after another term, is 15 squared over what? Over 48 squared. Let me write it as a square terms. Something like this. Okay, so you can add that extra term here, and here if I do that, it is going to be more accurate. It's probably going to follow something like this. It's never going to reach that blue one perfectly, but the more terms you use, the better it's going to be. So hopefully this video was useful to you, and I'm going to share the Simulink file and this MATLAB code for you, so you can use them and learn more about the nonlinear pendulum and the period of oscillations of that. Thank you so much for your attention, and I will see you in my next lecture.